Welcome 8th graders to the Dallas Independent School District STEM Environmental Education Center. We'd like to give a special welcome to the young men at the Young Men's Leadership Academy at Fred Florence Middle School. Thank you so much for registering for today's virtual field trip with us. We wish you could be here in person, but we're going to do our best to make you feel like you're here through a virtual field trip experience. If you are watching this and have not registered for this field trip yet, you can still do that by going to www.tiny.cc/EEC register. And once you get there, you can fill out a form to get yourself or your class registered for this field trip. We only use that information for our attendance purposes. Today's field trip is going to be about chemical formulas and reactions. During this virtual field trip, students will investigate how evidence of chemical reactions indicates that new substances with different properties are formed and how that relates to the law of conservation of mass. So first, you're going to see a chemical reaction that involves the production of a gas. That'll be led by Mr. Ramirez. Next, you're going to see another chemical reaction, but this time it involves a change in temperature, and that will be led by Mr. Monroe. Third, you will see another chemical reaction that involves a change in color, and that will be led by Ms. Nash. And last but not least, you are going to see a chemical reaction that involves the production of a precipitate, and that will be led by Mrs. Fuller. While we're doing all of these chemical reactions, you can ask us questions. You do that by going to www.tiny.cc/EEC-question-answer, and there you'll fill out a very short form where you can type in your question and submit it to us. You can ask us as many questions as you like, and we will do our best to answer all of them in the time that we have with you this afternoon. So let me stop sharing my screen here and turn it over to Mr. Ramirez, who is going to get us started with the production of a gas.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about chemical reactions and the production of a gas. So before we get started, we're going to have to understand what a chemical formula is and how to read it. So a chemical formula is just a combination of chemical symbols and numbers that represent a substance. So for example, here's an example of a chemical formula here. We see H2O. So we know H2O is simply water, but this time there's a big number in front of the H. That big number is called a coefficient, and it's simply telling us how many molecules of that substance there are. So since there's a 2, that tells us that there are 2 water molecules in this chemical formula. So that big number is the coefficient. Then we have a tiny number. The tiny number is called a subscript. So the subscript is just telling us the number of atoms there are for a particular element. So since the subscript is underneath the H, that's telling us that there are 2 hydrogen atoms. So when we look at different chemical formulas today, be aware of the coefficient and the subscripts. And if you don't know what a chemical symbol represents, you can always reference a periodic table. So the periodic table will tell you the symbols and the element that it represents. So we're going to start off talking about chemical changes today. And a chemical change is simply when one or more substances change into entirely new substances with different properties. So I'm going to go ahead and share my screen, and we're going to look at an example of a chemical reaction involving baking soda and vinegar. So let me get our PowerPoint running, and then we'll go ahead and start. So y'all are all familiar with the experiment with baking soda and vinegar, but we're going to go more in depth with it and how it uses chemical symbols. So our reactant is baking soda. Baking soda is also known as sodium bicarbonate, and it has 6 atoms total. So let's see how we got 6 atoms. So we have that subscript here, and that subscript is telling us that we have 3 oxygen atoms. Now the other symbols don't have a subscript. So if there's not a subscript, it's just understood that there is 1 atom. So for example, carbon has 1 atom, hydrogen has 1 atom, and sodium has 1 atom. So if we add up all of those atoms, there's 3, 4, 5, 6. So that tells us that baking soda has 6 atoms. Now this comes in handy because when we start balancing equations, the number of atoms in your products is also going to equal the same number of atoms in your reactant. So that's why it's important to understand how to count them. So for our baking soda, what I simply did is I put some baking soda inside a balloon and I weighed the mass. So in this diagram, we can see that the mass of the baking soda and the balloon is 11.4 grams. The other reactant that we're going to be using is acetic acid. Acetic acid is just vinegar. And vinegar, what I did is I put the vinegar inside a graduated cylinder and I weighed it, and it has a mass of 28.1 grams. Now, if we look at the chemical formula for acetic acid, we can see that it has 8 atoms total. So 2 plus 3 is 5, 5 plus 2 is 7, plus that 1 gives us 8. So we had the 6 atoms for baking soda and the 8 atoms for vinegar. So that means our product should have 14 atoms altogether, because 6 plus 8 is 14. So what I did is I took the balloon filled with baking soda, I placed it upside down over the graduated cylinder with the vinegar. The baking soda mixed with the vinegar, and we're gonna see a reaction. The reason I use that balloon is because I'm trying to hopefully capture the gas that's going to be produced. Now take a note at our picture here. The combined mass of our balloon with baking soda and our vinegar and the graduated cylinder, the combined mass is 39.5 grams. Now I used a digital scale, but at school you could also use a triple beam balance. So I'm gonna go ahead and show you guys a video of the actual experiment, and y'all are gonna observe to see what happens. I know it's hard to hear, but if you do it in person, you can hear a definite fizzing sound. So think of the sound that you hear when you pop open a can of soda, you hear the fizz. I also know that there's gas production because I also see the bubbles. So you can see the bubbles moving around in the graduated cylinder after we mix the two reactants. So the fizzing sound and the presence of bubbles indicates that we have a gas production. Plus, you guys should have seen that the balloon inflated. So you should have seen that the balloon inflated, and that inflation also tells us that we have a gas production. So now we're going to go ahead and take a look at some of our results. So our next picture, we see that the reactants had a mass of 39.5 grams. Now, after the experiment, the products had a mass of 39.2 grams. So you might think, well, wait, that's the products, the final result, the mass was actually less. So why do you think that is? Because according to the law of conservation of mass, matter can't be created or destroyed. So why do you think there's a difference in masses between the reactants and the products? What do you think might have happened within my experiment? So I'll give you just a second to think about what might account for that loss of mass. So what I believe happened is I think some vinegar escaped the balloon. And I know that because I can see some vinegar drippage here on the graduated cylinder. And when I touched the graduated cylinder, it was also wet. So vinegar escaped the balloon. Therefore, I think some carbon dioxide gas was also able to escape the balloon, resulting in that 0.3 gram difference from the products and reactants. So just know that in a perfect scenario, the mass of the products and the mass of the reactants will be the same. And here's another picture as evidence of what happened. Some of my gas escaped and some of the vinegar also escaped as well. So another thinking question for you guys is, does the presence of bubbles always signify a chemical change? And then explain your answer or justify it. Another example of chemical changes would be something called elephant toothpaste. And so here's a website from sciencebob.com, and they're using hydrogen peroxide. Now they're using a different grade of hydrogen peroxide. It's a 6% grade, so it's different than what you would find at the grocery stores. But they're using hydrogen peroxide, and they're mixing it with yeast, and that's causing the hydrogen peroxide to break down, resulting in the chemical reaction that you're seeing here and in the chemical reaction that you're seeing there. So there's some cool YouTube videos that you can look up online to see how hydrogen peroxide reacts with a catalyst, yeast. And again, whenever you do any science experiment, always make sure you have adult supervision and you're following safety guidelines and you're wearing your safety gear, such as gloves or goggles for protection. So that was the elephant toothpaste. Now here's the scientific chemical equation for what you see going on. So my question for you guys is, balance this equation for the decomposition of hydrogen peroxide in elephant toothpaste. So here's the chemical formula for hydrogen peroxide. When we add yeast, that catalyst, this is the resulting product. So given this information, what is the missing coefficient that would go here? And what is the missing subscript that would go here? So you can take a moment to just write it down or take a picture with your phone. And again, it's important to know that a catalyst is, in this case, would be yeast, and a catalyst is just a substance that increases the rate of a chemical reaction. So there's your challenge question. And I forgot to go back. I forgot to show you guys one of the other slides. So we were talking about the baking soda and vinegar. This is the final chemical equation for that baking soda and vinegar experiment. So we have our reactants, the baking soda, we have our vinegar, the products, the result of that experiment, sodium acetate, and water and carbon dioxide. So the gas that was trapped inside the balloon was carbon dioxide. Water was also produced, as well as sodium acetate. Now we talked about balancing equations. So remember, the reactants had 6 atoms for baking soda, 8 atoms for vinegar. So that was 14 atoms total. So that means that there has to be 14 atoms in our products as well. And we can see that there are 8 atoms here in sodium acetate, 3 atoms for water, and 3 atoms for carbon dioxide. So if we add all those together, we do get 14. So that means we do have a balanced equation, and it does follow the law of conservation of mass. So that's just how we would demonstrate the baking soda and vinegar experiment. Now, the last experiment we're going to do involves chemical reactions in our everyday life, and it's involving acid rain. So acid rain is just slightly acidic rain. It has a pH of 4. And the reason it has that slightly acidic quality is because of an increase of sulfur dioxides and nitrogen oxides from burning fossil fuels. So typically clean rainwater has a pH of 5 to 5.5. So when we have all that air pollution, it's affecting water quality and the rain. So that slightly acidic rain will actually affect the pH of soil, which will affect the tree growth. It also affects statues and buildings because it will dissolve certain sedimentary rocks. And it also dissolves limestone and porous rock, creating voids and cavities. So that's what we have, that's what causes the sinkholes. So to demonstrate this effects of acidic rain, I'm going to stop sharing my laptop screen, and I'm going to share my iPad screen so that I can hopefully show you guys a video of another experiment. So let me get that started. So I'm going to share my iPad. And let me just put in the code really quick, and we should be good to go. Okay, so here's our setup, and let me just show you our camera. So here we have Eagle Ford shell. So Eagle Ford shell is just a type of sedimentary rock, and there's a large outcrop of this type of rock about 6 miles west of Dallas, and it has a high carbonate content. So what we're going to do, we're going to demonstrate the effects of acid on some of our sedimentary rocks. Now, the type of acid we're going to be using our weak acid vinegar. And I'm just going to pour some vinegar on top of this shale. And I know you probably can't hear the fizzing, but I can hear the fizzing. And I know y'all can definitely see the bubbles that are forming. So this had a similar reaction to the baking soda. So baking soda also has a high carbonate content, and that is why it reacts to acids like vinegar or the slightly acidic rain that some areas might experience. Now here's a bigger chunk of that shell. We'll repeat the same experiment. So why do you think the bigger chunk of shell didn't have as great as an effect as the crushed up pieces? So that's a good thinking question there. Now, the reason we have this shell is actually because we use a lot of this shell in our fossil programs here at the Environmental Center. Students can find shark teeth. So just like this one that's found here and all these crushed up pieces that are found here. So shark teeth and other aquatic fossils are actually very common here in Texas because Texas was underwater millions of years ago. So that's how come we can find these fossils. So I'm going to go ahead and stop sharing our screen. So let me move back over here. And that is all I have for you guys today for chemical changes and gas production. We're going to go ahead and pass it back to Mr. Broughton, and he's going to answer any questions.
Thank you, Mr. Ramirez. I'm going to share my screen real quick and show two more things that can be seen by water dissolving rock, and that is stalactites and stalagmites in caves. If you look at all these pictures, you can see there's rock that appears to be hanging from the ceiling, kind of like an icicle does if it freezes, and also rocks on the floor that are growing upwards. Those are called stalagmites. The ones hanging from the ceiling are stalactites, and if they meet, then they're called a column. But what happens is slightly acidic water dissolves rock, seeps through the ground and into a cave, and then once it stops raining, the last drip will dry on the end of a stalactite and make it just a little bit longer. So they take hundreds of years to form. So do the stalagmites, so do columns, but they do form over time and make some pretty beautiful rock formations inside caves. All right, I'm going to stop sharing and we're going to go to the next chemical reaction, which involves a change in temperature, and that will be led by Mr. Monroe.
Good afternoon, students. My name is Mr. Monroe, and my portion of the virtual field trip that you're participating in with us today is to kind of help you guys explore the reactions that may cause a temperature change. Now, those reactions doesn't necessarily mean that a new substance is going to be formed, but it is an indicator that something is going on that could form a new substance when that temperature changes. I'm going to be using two compounds in a mixture. The first compound that I'm going to be using is called calcium chloride. And I have some of that in this container here. The other molecule or compound that is going to be involved in the mixture is something that is very essential to life on our planet, H2O. You guys know that that molecule is actually, or the compound, it is called water. Here before you, I have two beakers that actually have 200 milliliters of H2O in them. Also in those beakers, there are thermometers. The standard thermometer or a regular thermometer that you would use, and it is marked off in Fahrenheit and in Celsius. And I'm going to compare the readings on those thermometers at this moment. Okay, we're looking like 76 degrees Fahrenheit. This one is also 76 degrees Fahrenheit. Now, once we start our lab or our experiment, I'm going to take those thermometers out, and I will be using what we call a digital thermometer that has a probe on it. It's going to give me a quicker and faster readout and could be a little more accurate. You just don't know. Now, when we consider a reaction that's going on with the two compounds, we're going to refer to those mixtures as the system. And we're also going to refer to the beakers as the surroundings. Let me go ahead and let's get started. Now, before I get started with this compound, which is calcium chloride, it is a compound that has minimal health requirements. It's not real dangerous, but it's something that you need to be very careful with because it is in granular form, and if you ingest it or you inhale it, it could be detrimental to your health. It does not have a strong acidic response to your skin or anything, so you notice I'm not wearing gloves. But what I do have on is a pair of goggles, because I would hate for one of these little grains to actually get into my eyes. I could be in trouble. So what I'm going to do, put a couple of tablespoons of calcium chloride in this beaker. In this beaker, that's the second one. One in this one. And two in this one. Now I'm going to recap this compound because I do not want to spill it. The next thing I'm going to do, I'm going to mix it. We can see that it's turning the clear H2O into sort of like a milky color. And I can tell by touch that something's going on in this beaker. There is a temperature change going on because the surroundings are starting to warm up. I'm going to stir this one up, get it to dissolve. Pretty well dissolved. They're about the same color too, aren't they? Well, I'm going to get the digital thermometer out. I'm going to take a reading in both in Fahrenheit and Celsius. So, take a reading in this one. You can see the temperature is jumping real fast, guys. Kind of fluctuating. Okay, the temperature in this beaker is now 89.0 degrees Fahrenheit. In Celsius, it's 32 degrees Celsius. Let's go over here and see what's going on in this other beaker. We'll go Fahrenheit first. Wow. This one now is up to 92 degrees Fahrenheit and it's climbing 33.6 degrees Celsius. So I'm wondering, the question, did I actually put more of the calcium chloride in this beaker? Maybe I should have leveled it off like I normally would. So I'm kind of thinking that's why we have a variance in the temperature. But there was indeed a temperature change, students. And you know, the type of reaction that we have witnessed here with the H2O and the calcium chloride, that is called an exothermic reaction. That type of reaction is in the releasing of heat. Now, there's another type of reaction that actually indicates there's an absorption of heat. It is called endothermic reaction, an endothermic reaction. Now, the rule of thumb commonly is that when chemical bonds are formed, heat is released. And when chemical bonds are broken, heat is absorbed. One such example of an ectothermic reaction that we see around us daily is combustion. And we know that happens in automobile engines and various engines that use the burning of carbon containing compounds using oxygen and air produces carbon dioxide, water, and lots of excess heat. Of course, a good example for an endothermic reaction would be the sun's heat being absorbed by a plant and that plant using that heat energy in the process of photosynthesis to convert CO2, carbon dioxide, and water into glucose or oxygen. Students, hopefully what you observed here kind of gives you an idea of two different reactions that involve a change in temperature. We know that one is going to release heat, the other is going to absorb heat, and hopefully you understand that. And if you have any questions, I'm going to turn it back over to Mr. Broughton, and maybe he can answer those questions for you. Okay, Mr. Broughton.
Thank you, Mr. Monroe. The question that came in is that chemical dangerous? And again, that chemical is calcium chloride, and it can be dangerous, especially if it's ingested, or that's a word that means swallowed. If you were to ingest calcium chloride, it could burn your mouth and throat. It would make you very thirsty because calcium chloride is a kind of salt. You might vomit, you'd have a stomach ache, and you could end up with low blood pressure, probably not your whole life, but while it's first ingested. So you definitely do not want to ingest calcium chloride. You notice that Mr. Monroe wore goggles to make sure it stayed out of his eyes, and also did not taste any of it. You don't even want to get it on your skin because since it is a salt, it could really dry out your skin. So it's always important to be safe with the chemicals that we use. All right, now we're going to move on to a new chemical reaction that involves a change in color, and that will be led by Ms. Nash.
Welcome to my classroom, and today we're talking about color change. And it's my favorite time of year. I don't know about you, but I'm so glad it's not going to get any hotter because it's fall. And we know that, besides the fact it's not going to get hotter, we can see the leaves changing color. So this is a biochemical change. So the green is disappearing. That green chlorophyll is breaking down. And when it breaks down, other colors that were in there all the time, the yellows are revealed. Okay, so we can see various different colors arising. Okay, and all around us. Okay? That means that the chemistry of the leaf is changing. Okay? Now, we can also, another one of my favorite things is rusting junk. I don't know why. So fascinating to me. And so I found this old hammer out there and I brought it in. It's kind of stopped rusting indoors because it's not very wet. But this nice strong steel hammer, if I left it outside, put it back out, it would gradually just dissolve away, not dissolve, flake away. It would be rusting. So rusting is a chemical change. So you can see my two railroad spikes, one not very rusted, one pretty rusted. So what's happening? The water is reacting with the iron, and oxygen in the air is becoming attached down here. It's no longer a gas. So I put some steel wool in here with water. I put a balloon on top. And then as it rusted, that oxygen that was taking up all kinds of space, it's a gas, right? It became a solid and it created a vacuum inside the little flask here and it pulled the balloon down. Pretty amazing. I tried to run a little experiment, but my results were inconclusive because theoretically, or in actuality, salt water should rust things faster. This is an electrolyte. It means that the ions are moving, changing faster. But I had one with salt, one with plain water, and it looks pretty much the same. Okay. But except you might try it, and maybe you would have a better result than me. Another thing kind of interesting is that rust keeps on happening. So this outer part will flake away. And in here, we have all these flakes that were in the basket I had my rusting junk in. And as new iron is exposed, it will keep on rusting, okay, until it's all gone. And you also may see soil around with this kind of color in it. That means that it had iron in it, and now it's rusted. So, pretty interesting. Now, a little experiment here, or a demonstration rather. I've got 4 little beakers with vinegar, distilled water, tap water, and baking soda. Now we know that vinegar is a weak acid, and we know that baking soda is alkaline, basic. So I'm going to put a little bit of this chemical called bromothymol blue. It's a pH indicator, meaning acidity. So pH is the concentration of hydrogen ions. Now, see here? Yeah. So my baking soda turned pretty blue. My tap water is kind of a light blue. Let's see. Let's see. Because interestingly, our water here is pretty basic, pretty alkaline. Because the rocks that it goes through are quite alkaline. Now, distilled water, just a little acidic. In our vinegar, come on, vinegar. Our vinegar is, again, a little bit more acidic. Now, I thought we'd also test, because we need to know what the water quality is, because it affects our plants, our drinking water, and our fish and our froggies. So I brought their water out. So this is my fish. Let's see, if that water is going to be basic or is it going to be acidic. And it's a little bit acidic. So even though the water in there is tap water that I treat, it is, hold on, pretty basic actually, pretty good. Neutral though. The froggy's water is a little bit basic. So I might need to work on the chemistry of my aquariums, okay? Now, you can make your own pH indicator at home with a blender and a red cabbage. And then you can do some really interesting tests to see what you're drinking. So I've got, again, baking soda, tap water, distilled water, and soda. And vinegar. Let's see. And this is my red cabbage. I ground up a hunk of red cabbage with water in a blender, and I strained it out. And I ended up with it. Kind of stinky mixture. Rainbow. So the acid get kind of red, and then we have a little rainbow on down to the blue. And again, why do we care? Well, this soda might be dissolving your teeth, okay? So be careful. Now here's another little experiment. Excuse me, or demonstration. I've got water in here and a straw. And I'm going to put my fast dwindling supply of bromothymol glue in here. And I think I'll put on my goggles just in case I splash some of this stuff in my eyes. And I also have to remember not to suck. So I've got my bromothymol glue, okay, in our just tap water. So here we go. So it's kind of alkaline, right? Just our tap water is a little bit alkaline. It's also a test of my lung capacity. Okay, air, but can you see the color has changed? And now it's a little bit acidic, okay? A little bit acidic. This color is indicating that I have changed the composition of the water, the chemistry of this water. So what happened? Okay, H2O, water, plus CO2. When I breathe out, I've got carbon dioxide in my exhale. And then, what am I making? I'm making carbonic acid. Okay, not good. Okay. So acid, as we know, can dissolve things. Okay? Dissolve your teeth, dissolve cells. So as we put more CO2 into the atmosphere, it goes in the oceans in particular, and it's affecting the acidity of the ocean, the chemistry of the water in our oceans. And of course, that affects all the life in that water. So we need to be careful and think about all that CO2 that we're producing as if there were no tomorrow. So enjoy fall and think about the chemistry that's involved. And if you have any questions, Mr. Broughton would be glad to answer.
Thank you, Ms. Nash. The question that came in was, does a color change always indicate a chemical change? And no, it does not. If you just pour some food coloring into a glass of water, that is a physical change because you are changing the physical color of the water, but you're not changing anything chemically. So that would just be a solution involving water and food coloring. But color change, as you saw from all of Ms. Nash's investigations there, can indicate a chemical change. So if you see a color change, it doesn't automatically mean one thing or the other. You're going to have to look at it and think about it and see if you can figure it out. All right, now we're going to move on to our last chemical reaction. This one involves the production of a precipitate, and it'll be led by Mrs. Fuller.
Hello, boys and girls. We're going to be talking in this last segment about precipitates. When you were in the 4th grade and you were studying the water cycle, you learned about precipitation: rain, snow, sleet, and hail. Well, what does precipitation do? It falls out of the sky, falls out of the clouds. Well, we have precipitates and other venues of science as well. And in chemistry, we call precipitates things that fall out of solutions. So when two aqueous solutions react, they sometimes form solids in the solution, and that would be our precipitate. The solid precipitate is an insoluble ionic acid. That means it can't be dissolved again. So let's talk about solutions before we do our demonstration. Now, when you were in the 6th grade, you learned about solutions, suspensions, colloids. I'm going to remind you of the characteristics of solutions. A solution is a special type of mixture. It's homogeneous. It's the same from top to bottom and side to side at the molecular level. You cannot filter out the parts, the solute that has been dissolved in the solvent. Now, a solution is composed of 2 or more substances. The solute, I'll show you a card so you see it. The solute is a substance dissolved in another substance. Now, and the other substance is known as a solvent. Now, back when you were in the 4th grade and you were learning about characteristics of water, you learned that water is the universal solvent. And the reason for this is the polarity of the water molecule. So usually in solutions, the solvent is the one that there's the most of. Now, particles cannot be seen with the naked eye in a solution because they're at the molecular level. They're not big hunks of pieces of things. A solution does not allow beams of light to scatter. It's transparent. A solution is stable and the solute cannot be filtered out. I can't pour a solution through a filter and get the solute out because it's at the molecular level. And it's composed of only one phase. Now, the ability of a substance to be dissolved in a solvent is called solubility. Some things are more lend themselves more to this than others. So let's go ahead and look at a little demonstration. Oh, before we do that, let's balance our equation here, okay? So this is what we're going to start with. We're going to start with silver nitrate. So silver nitrate has 5 atoms. So let's count them. 1 for the silver, 1 for the nitrogen, and we've got a subscript of 3 here on the oxygen. So that's going to be 1, 2 plus 3 is 5. So we've got 5 here. Then we're going to add to it potassium chloride. So potassium has 1 atom, chlorine has 1 atom. So the potassium chloride equals to 2 atoms. 5 plus 2 equals to 7. So when you put these together, it's going to yield. Remember that little arrow means yield. It's going to yield these 2 products. Silver chloride has 2 atoms, 1 for the silver, 1 for the chlorine, and potassium nitrate has 5 atoms, 1 for the potassium, 1 for the nitrogen, and look, we've got a subscript of 3 here on the oxygen. So it's going to be 1, 2 plus 3 is going to be 5. 2 plus 5 is 7. So they are balanced. 7 on on this side, the reaction part, and 7 on the product part. Okay, so let's go ahead and demonstrate this. Let me pull my demo table around here. This is our silver nitrate. This is our potassium chloride. As you can tell, they're both clear. You can't see any particles because the materials in them are at a molecular level. When we pour the potassium chloride into the silver nitrate, it's immediately going to become cloudy. I'm going to stir it, and as they mix together, they will begin to form a precipitate. Precipitate is going to be silver chloride. And we can't dissolve it again, remember. All right, so this is very toxic. So I'm prepared to keep safe. So we're going to start stirring this. I'm going to stir it a little bit more before I show it to you to increase the likelihood that you can see these particles at the bottom. All right. Let me come around here to the camera. So I'm going to show you the bottom of this. Can you see those particles forming? That's a precipitate. That's silver chloride right down there. I do have some that I made earlier today. Can you see that solid down there at the bottom? When I first made it, it was pure white, chalky white, but now it is turning purple. Okay, so this does have a color change eventually. So there is our precipitate. There are other kinds of precipitates other than those from chemical reactions. I don't have time to go into those. Some of them are physical manifestations rather than a chemical one. If you want to look something up about that, you might want to look up the Dead Sea and the salt crystals that precipitate out of the bottom layer. So if you have any questions about precipitates, I'm going to turn it over to Mr. Broughton. Thank you.
Thank you, Mrs. Fuller. The question that came in was, are those chemicals dangerous? And yes, they are. Mrs. Fuller mentioned that they are toxic, and that is why she wore gloves, a lab coat, and goggles. Those are important things to wear anytime you're working with even chemicals that are not dangerous, like salted water. If you develop good safety habits, working with less dangerous things, you'll have those habits with you when you work with more dangerous things in high school and beyond. All right, I'm going to share my screen here with you one last time. And we're going to do a quick recap of what we did today. So today we investigated chemical formulas and reactions. During this virtual field trip, students investigated how evidence of chemical reactions indicates that new substances with different properties are formed and how that relates to the law of conservation of mass. Because remember, we cannot create or destroy matter during chemical reactions. First, we saw the production of a gas that was led by Ms. Ramirez. Next, we saw a chemical reaction that involved a change in temperature that was led by Mr. Monroe. Third, we saw chemical reactions involving changes in color, and that was led by Ms. Nash. And we just saw the production of a precipitate led by Mrs. Fuller. Thank you so much for joining us this afternoon. We appreciate you taking the time to learn about chemical formulas and reactions with us. And we would like to know what you think about today's field trip. You can let us know by going to www.tiny.cc/EEC feedback and filling out a short form that takes about 1-2 minutes at the most to fill out to let us know what you thought. We look at your responses and comments to help improve what we do out here. We hope to see you again in about 3 weeks. Have a great rest of your day, and we'll see you next time. Goodbye.